let me remind you what we did last time. We were working on stochastic gradient descent, and then we looked at a variation of that, a variant of that, which changes the step sizes during the run of the optimizer. So that was called stochastic line search. It is from this paper from NIPS, Vaswani et al. And painless stochastic gradient. It's from 2019. It's fairly a recent paper. And if you remember, the idea was doing an Armijo line search and deciding the length of the step size by that. What was Armijo line search? Very quickly, you would start with an maximum step size, let's say alpha k, and then what you want to do is you want to find the biggest alpha k, which is smaller than equal to alpha max, such that alpha k satisfies this equation. So what was this? So fik stands for the loss function evaluated at the point xik, yik, ikth data point, and then gradient fik is a gradient of that function. Basically what you do is you take a stochastic gradient descent step, and then calculate the function at that point, and you want the new point smaller than the value at the old point. You should have omega k here, and this, you want this distance to be sufficiently small meaning it should be smaller than some constant times the step size times the the norm squared of the gradient of fik at omega k. And if this is satisfied, you like that point, you like that descent, and you go with the algorithm, you move to that point and take another stochastic gradient step. But if this condition is not satisfied, then you say, okay, this step size probably was too big, let's reduce the length a little bit. You multiply it with some gamma, like something close to 1, like 0.9, and then now you have a smaller, okay, I'm talking about a way to find this alpha k. It's called backtracking. Every time if this Armijo condition is not satisfied, you decrease the length by 10%, and then try this and check this condition again, and if it works, you move to that point. Otherwise, you do backtracking. Yeah, you again reduce the size by the same amount. So hopefully, in a way, this will approximate the solution, the biggest solution of this inequality. But the problem with this is, of course, every time you check the condition, you have to calculate the value of the function at this new point. And with these large-scale machine learning problems, calculating the function's value, even for just one data point, takes some time. It's not negligible. So if you want to do it again and again, it will hurt the performance of your algorithm. And what else? And I forgot to say that the C here is just a hyperparameter. You use cross-validation to choose which C works best for your data and for your problem, for your model, for your data, and so on. What else to say here? That was the algorithm. All right, and then this is the algorithm in short. You start with a point, you choose a maximum number of steps, and then you give these constants to the algorithm, and then you choose an integer randomly, uniformly from the data point. you choose a data point uniformly randomly, and then take a step, check the Armia condition, and try to find the step size which biggest step size which satisfies the Armia condition. And then, in order to not to start from the same alpha maximum the next time, because you expect a similar step size would work in the next step too, instead of starting from alpha max, you update alpha max as the alpha k you got from the Armijo line search. And then you start from this point in the next iteration. And this will quickly diminish, and your algorithm will stall for a long time, and it will take forever to reach to a nice optimizer minima. That's why once in a while you want to reset your alpha max and return to the original value. All right, camera lost me again. So this was stochastic line search, and we looked at its performance, and we also looked at its theoretical convergence rate on for non-convex objective functions, and starting from an fixed step size. And then we talked about a variation of that, stochastic line search with model building. Again, this is a recent work by me, by Birbil, Onay, and Öztoprak. And the idea is similar. You take a stochastic gradient descent step and then check the Armijo condition. But instead of doing backtracking, what you do is you build a model at that trial point, the step you took. And if the Armijo condition is not satisfied, if the Armijo condition is satisfied, you take that point as your next point. If it's not satisfied, you build a model on these 2 points, the original point and the trial point you take. And this, you go to the minimum of this model. And there's only one step here. You make construct the model only once, and then choose its minimum as the next step. So this was the algorithm. Again, you start at a point, take an stochastic gradient descent step. You choose the new point, regard this point as just a trial point. If the Armijo condition is satisfied, you fix that point and move to the next iteration. If not, you build a model, find this minimum, you find the minimum analytically, calculate the minimum, and then you take that step and move to the next iteration. And remember that these deep learning models come with groups of parameters. They don't have one big vector of parameter, but they divide it into groups, and you do this for each group, and you come up with a different step for each of these groups. The difference between the previous approach and the model building approach is, in the backtracking, you always stay in the same direction, but you are decreasing the step size. Here, when you build the model, actually you are decreasing the step size, but also you are changing the direction of the step. So that's one of the main differences between model building and backtracking approaches. And all right, last time I didn't give a convergence proof for this algorithm. All right. So how can we show convergence of an algorithm like this? Actually, what I'm going to introduce today is a general framework which can help to show convergence of methods where you just don't multiply the gradient by a scalar to choose the length of the step, but also you multiply it with a positive definite matrix, so you change the direction also. So this method, SMB, stochastic model building method, can also be considered that way. Basically, again, what we do is whenever the Armia condition is not satisfied, you build a model and find its minimum point, and then you move to that point. But this process here can also be written as kind of a stochastic gradient descent, but instead of, you have a matrix here which changes the direction of the gradient step, and it can be shown that for SMB this matrix can be calculated by this matrix where there are some constants. So I'm not just going to skip what the constants are. So you can write it as a matrix. That you can write this step as this step where HK is a positive semi-definite matrix, and it has some other properties that we will use to show convergence. In general, if you have a square symmetric matrix, we will call it positive semi-definite if for any omega in Rd, for any vector omega, the inner product of omega with A times omega is always bigger than or equal to 0. And if this is strictly bigger than 0 for non-zero vector omega, then A is called positive definite. All right, just to remind you. And our HK in SMB has this nice property that in every step you create, calculate this matrix, it changes the direction or even the length, decreases the length. And this matrix is symmetric, positive, definite, and you can find two constants, kappa underline and kappa overline, positive constants, such that this inequality is satisfied, and this inequality is not smaller than or equal to, actually A kind of smaller than or equal to B, means B minus A positive semi-definite. All right, and in our paper we show that actually our matrices satisfy, okay, this inequality is satisfied for all K, so it's uniformly on K, and we can show that actually it is satisfied by these constants. But why this property is kind of enough for showing convergence? Let me show you those results. All right, again, we want to minimize a function f of omega given by a finite sum, the empirical risk or the expected risk. And then before we were taking gradient steps where the gradient is either the gradient of the loss function at one data point determined by this random variable xk. This xk is a random seed. It can choose one data point, or it can choose nk many data point, and then you take average of the gradients. This is called the mini batch method. And then now in our analysis, we need to change this. What we are going to do is we are going to multiply these vectors by this matrix, HK. All right, the HK is a positive semi-definite matrix or definite matrix. And let's assume it is independent of K. So a new assumption, and it satisfies this property for positive definiteness in terms of positive definiteness. All right, so we are going to assume these three things, and we are going to define our gradient, stochastic gradient descent the same way. The only thing is now G is not just an estimated gradient, it is HK times G. All right, so our actually analysis from before also works for this. pretty similarly. Let me remind you how we proved this before for regular gradients, not times a matrix. But let me remind you that in our method SMB, actually this HK is either the identity matrix when the arithmetic condition is satisfied, you don't change the direction, you just keep that. So it's just identity matrix, or it's a positive definite matrix. And since we are looking at groups in deep learning, at least, we are looking at these groups of parameters. For each parameter, you come up with an submatrix, and this whole process turns into a diagonal matrix, block diagonal matrix. Each of these blocks is positive 7 definite. So HK is either identity or this block diagonal matrix, and it satisfies this positive semi-definite definition, this inequality. All right, but okay, in general, let's assume is HK satisfies these conditions here. And then let's see why our proof from before adapts very quickly to this new case. So our first assumption was the gradient of f. F is differentiable, continuously differentiable, and gradient f is Lipschitz continuous. That stays the same. And remember that under this condition, we had this lemma. We are going to use this lemma, but now instead of just average gradients, we will have HK times the gradient, stochastic gradient. But there is no assumption there what G is, so we will use this lemma. And then we are going to define the variance of the stochastic gradient. So it's just the expected value of the squared norm of the stochastic gradient minus expected value of the gradient squared, norm squared. Then if you define a variance like this, I'm going to give new assumptions for my algorithm, this new kind of SGD, which also covers this HK times the gradient method. As before, f is lower bounded by f inf, and then there exists constants mu g. Oh yes, this should be a capital G. Mu g bigger than equal to mu, which is n bigger than 0, such that the inner product of the real gradient of f and the expected value of the stochastic gradient is bounded from below by an expression like this. It's mu times norm squared of the gradient f, full gradient. We want this, and then we want the expected value of the full gradient, hk times the gradient in this case, expected value of g in norm to be smaller than equal to this constant mu g times the norm of the full gradient. And then we want two positive non-negative constants m and mv such that for all k, the variance of this g is smaller than equal to m times mv times the norm square norm of the full gradient. And again, G here does not stand for just the mini batch gradient or stochastic gradient, but it stands for HK times the gradient. So we want this to satisfy. And then once these are satisfied, then you can easily show that this is satisfied. This was the condition that we had before for showing convergence of the regular stochastic gradient steps. All right. So with these extra conditions, since our G definition of G has changed, with these extra conditions, actually we can show this lemma. It's the same, so I'm not going to go over that. just used those to show that the second lemma we have seen before was the same thing except one here. Now we have mu, and it just comes from this property here that we assume that gradient of f of omega k inner product expected value of k g of omega k is bigger than equal to mu of gradient f of omega k non-squared for some mu positive. All right, so and in the previous lemma, we were just assuming that this is the gradient of f of omega k, since those stochastic gradients were unbiased estimators for the real gradient. But now we cannot say that because there is also an hk there. But so what we can do, instead of writing this as the norm square of f of omega k in this proof of the lemma 2, we can just say this is bigger than equal to mu times this. And it's under a negative sign, so this lemma 2 follows very easily by using this. And since this condition is already satisfied because of these conditions, by means of these conditions imply the second condition that we have assumed previously. So the proof really kind of goes through very easily. So we have this, and okay, and one thing is, of course, why our hk times g satisfies these conditions. And actually it's very easy to see that because okay, now our stochastic gradient is not just the gradient by this hk times, let's say, just do it for 1 point, the gradient at 1 point. So now this is our step in this new version of the stochastic gradient descent algorithm. And if you take the expected value of this, hk times then, since hk is independent of ck, then this just, you can just take it out and calculate the expected value of the gradient inside. But this is an unbiased estimator for the gradient, full gradient. So this is just hk times the gradient of f omega k. Therefore, if you look at this condition, this is just but by the definition of, by assumptions on hk, this is bigger than equal to, it's positive definite. And if you remember, k times I is smaller than equal to hk, then that means hk minus I is positive definite or semi-positive definite. So you can see that this is bigger than equal to this. There's no transpose, yes. And then this is just k times norm squared. So this condition is satisfied if you put b equals kappa underline. And then what else do we want? With our assumptions on hk, we can show that this first condition is satisfied and the second condition is satisfied because very similarly you have expected value cos k g of omega k cos k, all right, and norm squared. This is just again hk times the expected value of g k, let's say, and this is just smaller than equal, okay, this is just hk times the gradient f of omega k squared, and this is smaller than equal to kappa over line squared and then the gradient of f of omega k norm squared. So the second condition is also satisfied. And actually very easily you can also show that the third condition is also satisfied. So because of our assumptions on hk, we satisfy all these assumptions. So our new steps multiplied with hk satisfies this lemma, so we have this result. And then now we can give a convergence theorem for this new kind of stochastic gradient step. This is a modified version, of course. You multiply with an hk here, and then very easily, very similar to the case where we have the regular SGD, we have similar rates. Only thing changes is we have this mu appearing in the denominators. That's the only thing. So this is a framework for okay, so this is a framework where you change the direction of the gradient in the stochastic gradient descent steps, and you can show convergence. And I just gave the convergence result for non-convex objective function and the fixed step size that you would use in deep learning models, but you can also look at diminishing step sizes and strongly convex functions, you can give similar results. So the problem with SMB, just to mention briefly, is in SMB, the matrix calculated is, okay, satisfies this inequality in terms of positive definiteness, semi-definiteness, but unfortunately HK is not independent of GK, the randomness of the gradient, or CK in that sense. So to make this convergence result work in this case is what you need to do is, and you see this in other second order methods, that you calculate the matrix with a new batch which is independent of the previous batch. So you choose a batch CK and then calculate the stochastic gradient and the function value there, take the stochastic gradient step, and then check if it satisfies the Armio condition. If satisfied, you move to that point. If not, what you do is you choose a new independent random batch or independent index. Then you calculate the gradient with this new batch and calculate the gradient step, and you calculate all these values that you use in calculating the matrix, and then use that matrix to take the model step. In that case, now your matrix is independent of your GK, and then the proof works the same. So it falls into this framework. And now you have a little bit different algorithm. And if you look at the experiments with this, let's call this SMBI, where I stands for independent, where you choose HK with an independent batch, calculate HK with an independent batch. For MNIST data, you see that actually it behaves very similar to regular SMB method, a little bit worse, I would say, because it reaches to this good accuracy later than SMB does. All right, in terms of runtime. But when it comes to this problem, CIFAR-10 with this ResNet convolution neural network architecture, SMBI behaves pretty bad actually, a little bit better than ADAM, but worse than SLS, SMB, and regular stochastic gradient descent. But if you remember, and in terms of accuracy, if you remember, we had tried a little bit simple auto-scheduling by looking at the number of model steps in an epoch. And then we can see that with that scheduling, SMBI works, performs better than SLS on training loss. And if you look at the test accuracy, it behaves similar to SLS, a little bit close to SLS, but worse than SMB still. So actually what this says is dealing with an HK which is dependent on GK, actually it works better. So SMB consistently works better than SMBI, but we don't have a convergence result for that yet. Because of that dependence, we cannot calculate this expected value because HK is dependent on this and we cannot just take it out. So this is an aspect that should be examined for this algorithm. Anyway, so other second order methods falls into this framework also. And let's look at some examples on that. All right, so if you know classical optimization, there's this method called Newton method. What it does is this. In the stochastic gradient descent, in a way, what you do is you take a linear approximation to the function. And then, of course, when your function is just linear, you just go in the direction of the gradient, opposite direction of the gradient. It's where the function decreases the fastest, for regular functions too. But in a way, the opposite direction of the gradient actually gives you the minimum of that linear approximation. All right? If you choose a step size, then in that region, that's where the minimum is. What second order methods do, instead of looking at a linear approximation, they look at a second order approximation using the Taylor series. And then you can actually then you choose the direction where the second order approximation's minimum is. That's your new direction. And it doesn't have to be in the opposite direction of the gradient anymore. So how you do that is you solve this equality. This equality actually is the direction where the second order approximation's minimum is. So you solve this equality, but solving this equality is not that easy, because now you have the Hessian here, which is the second derivative of the objective function. It's an matrix. If your gradient is d-dimensional, then this is d times d dimensional matrix. And then you want to solve this equality for Sk. Well, in that sense, what you need to do is you need to calculate the inverse of this Hessian to solve it for Sk. And it is not easy if your function's dimension is big. And it's nearly impractical if your dimension is huge, like deep learning models. All right. So there is convolutional methods to calculate this solution approximately. Yeah, we are not going to see that. But there are methods which solve this equation approximately without really calculating the Hessian or its inverse. So, but this is really impractical when you have deep learning problems, optimization deep learning models. Then what you do is, instead of calculating the Hessian or the gradient, we cannot even calculate the gradient, right? It takes so much time. Yeah, we can, but just we try to do it just for a few data points, not for the whole set. So what we will do here is we will take the same approach calculating the gradient. We will take an mini batch Sk, and then calculate the average gradient on that mini batch. And we will take another mini batch to calculate the Hessian on that data set. But even this takes a lot of time if your dimension is huge. Anyway, but you can do that, at least for middle-sized problems, and this may work. And all right, so what you do is you solve this equality for these mini gradient and Hessian. And again, you can use these convolutional methods to find the solution, approximating the solution without really calculating the Hessian inverse. All right. And then once you solve this equation and choose the direction where the minimum is for this second order approximation, then you need to come up with the right step size. And right step size is, again, is chosen by backtracking. You find alpha k, which satisfies this equation. You find the biggest alpha k, which satisfies this equation. So you look at, you do backtracking as before. So this is called inexact Newton method. And even though you are using mini batches here, and what you want to do is you want to choose the second mini batch which you calculate the Hessian with, independent from the mini batch you calculate the gradient with, so that the proof works the same. Your matrix is independent of the gradient, and you can calculate the expected value of hk times the gradient. All right, but again, still you need to, even though you take a mini batch, calculating the Hessian is not easy at all. It takes a lot of time. So instead of calculating the Hessian with a mini batch, there are methods from state-of-the-art methods from classical optimization called quasi-Newton methods, where instead of calculating the Hessian and then solving that equation, maybe calculating the inverse of that Hessian, what you do is you come up with an algorithm which approximates the inverse Hessian, but it doesn't involve calculating matrices. It's called BFGS method. What you do is you use these pairs called curvature pairs. At each step, when you take a step, in the previous step, when you take a step, you record the direction you moved and then the length. You record the step you took in the previous step, and you record the differences between the first point and the second gradients at this first point and the second point of that step. And so you store sk and vk from the previous iteration, and then use them to update your approximate inverse Hessian in each step. So you start with hk equals to identity or your favorite matrix. There are methods to find the initialism matrix, different methods to initialize this process. And then in the previous step, you use that matrix to take the step. So in the next step, you use this curvature pair from the previous step to update your matrix, and then obtain a new one that you will use in that step, in the next step. And of course, this only involves the sk and vk, the gradients and the points from the previous step. So this matrix, when you apply it to the gradient, is independent from the gradient. So this analysis again works. And actually, you have to show that this hk is positive semi-definite. So you have to be careful how you choose these points. So there are methods. I'm not going to go into detail, but you can guarantee that this hk is always positive semi-definite and bounded from above and below uniformly by some constants times identity. All right, and so you can apply the method I have shown you to stochastic quasi-Newton methods. All right, and then instead of calculating differences of gradients at different points, sometimes what you do is, instead of calculating as the differences of the gradients at mini batches, what you want to do, sometimes the variance in this stochastic gradients is huge, and then this gives you a wrong estimate for the curvature in a way. So what you do is you use this inequality. The gradient is nearly the second gradient. The difference in gradients is nearly the second derivative times the difference in points. So it's definition of a derivative. So you can use this kind of approximate equality, and then instead of calculate the vk by this Hessian times the step length. But it is of course mini batch Hessian now. So if you choose SKH, a big mini batch independent of SK, then this may give you good information on the curvature of your objective function. And this is how you apply your quasi-Newton method. So I'm not going to go over that in detail, but there are a couple of improvements to the argument that you don't. One thing is, if you store every pair from the previous step and then update your matrix with those, at the end what you get is you need a lot of memory, and this is really hard on your computer. It may be impractical to do that, especially when your function dimension is very big. What you do then is you don't take record all of the steps, but you record only last m steps. All right. And then, so you choose a constant m, you record only the m steps. And with the stochastic quasi-Newton methods, what is shown works better is you don't take at every point, it's not just the last m step. What you do is you record the curvature pair every 10 steps or every 20 steps, and you take the last m many of them. So there are some tweaks that you apply to this method, and then you can show that it can work better that way. And you should check this paper on more information and here, and then you should check the references there if you're interested in second order methods in stochastic optimization. All right, last time we have seen a way to show convergence of these second order methods, a general framework for that, where in all of these cases that we have seen, you calculate the stochastic gradient and then multiply it with a matrix, and that's how you update your point. So you change the direction of your gradient. So now I'm going to move into another direction, starting with this theorem. It is the theorem I took from this paper that I have followed, used extensively in this course. All right, so what is this? It is actually a way to, okay, it is an analysis of what happens if we somehow reduce the variance of the stochastic gradients. If we can find a way to reduce them exponentially like this, so if the variance of the gradient at each step is diminishing exponentially, so it's always smaller than equal to m times I don't know this constant between 0 and 1 to the power k minus 1. So if x decreases exponentially, then with these constants, actually, basically what you can show for strongly convex objective function, but fixed step size, that your expected value of your steps minus the global minimum, actually the distance between them, you expect them to decrease again exponentially. So if you remember, the theorem that we have proved for strongly convex objective functions with fixed step sizes, this was converging to a constant depending on your step size. So we were not really converging to the global minimum, but to a neighborhood of that. All right, I'm going to skip the proof of this. You can find it in this paper. It's very similar to what we did before, just a little bit of manipulation, and then with induction you can get this result easily. So, but you have to choose your constant wisely so that this whole proof works, and this is how you choose your constants so that the proof works. So what I want to do is I want to look at methods which satisfies a noise reduction. This, you know, how methods that reduce the noise in the gradients. So I'll just look at a few. One is dynamic sample method, dynamic sample size method. So instead of choosing one mini batch size and stick with it all through the optimization process, all through the run of the algorithm, what you do is you increase the size of the mini batch in a way cleverly, so that you reduce the variance. What I mean of the gradient, what I mean is every step you choose an nk, that is the size of the mini batch, and you calculate the mini batch gradient. Then what you want is you want your gradient, the size of the mini batch, sorry, to grow exponentially with respect to some tau which is bigger than 1. That's what you want to do. And if your gradient's variance is bounded above with a constant m, then these new if variance of each gradient that is evaluated at each that data point is bounded above from a constant m, then if you keep on increasing the mini batch size, then your variance diminishes by nk, and if you choose nk growing exponentially, then your variance diminishes exponentially. So you can make this satisfy the condition of the previous theorem. One thing here is, since you are increasing the step size exponentially, if you do that, then your calculation cost also increases exponentially. But your rate of convergence is improving. So you actually, in order to balance the calculation cost and the rate of convergence, you need to come up with a good way and carefully selected way to increase these size of the mini batches. So it's not an easy process. You can come up with theoretical results how to increase that, but at the end, those theoretical results can also be hard to compute in terms of the given machine learning problem at hand, with respect to the problem at hand. So this is one way to, increase the convergence rate of our stochastic gradient method. So you increase the sample size. There is also other ways to do that called gradient aggregation. So what you do is you do not increase this every time except in the beginning. You calculate the gradient once for one data point, and then but you keep on storing them and updating your gradient with respect to those. Let's go over this method called Sega. What you do is you start with initial point and you choose a step size, fixed step size. Then in the beginning, you calculate the gradient of the gradient of the loss function at each data point at the point omega 1, at the parameter value omega 1. And then you store them into this omega gradient fi omega special, I in parentheses. So you store them. You do it for once, go over all the data points. And then at each step, you choose a j uniformly from 1 to n. You choose a data point uniformly from the training set. And then you calculate the gradient of the loss function evaluated at that data point you have chosen at the point omega k. And then now you set up your gk so that you take your step with it, such that first you use the gradient fj omega k, and then you use the gradient that you stored in the previous steps with respect with the index j, and you take the averages of gradients that you have already stored in the previous step, and then you subtract this one and add the average, and then set it as the gradient step. So you are averaging these gradients and then use it as the gradient that you use in that step. So averaging these, of course, diminishing the variance of these gradients. And then, since you have chosen this gradient at the data point xj, yj, you store it instead of gradient fj omega j in parentheses. So you change only one of these stored values, and then you update your point with this gk that you have calculated. And with this method, you can get pretty good convergence rates. But again, of course, you lose some computation power, computation cost. Although it looks on paper pretty good in terms of computation time and computation complexity, it really it's not clear that it suppresses stochastic gradient descent or not, but it has some good results on some problems. So this is one way you decrease the another way you decrease the variance of the gradients. All right, so this is all I'm going to say today, and actually this is the end of our class. Thanks a lot for coming.